The input bias current for real op amps is small, but not zero. Take for example this specification. This input bias current has a maximum of -2.2 microamps. What are the implications of this non-zero input bias current of an op amp? This input bias current gets converted to a voltage and amplified along with the input signal. It creates an error in the output signal, just like the input offset. This is what the input circuit of an op amp looks like. This is for a bipolar transistor op amp, and it has higher input bias current than JFET or MOSFET designs. The input bias current for input transistors Q1 and Q2 is not zero if their bases are grounded. How do we model the input bias current of an op amp? Let's refer back to our ideal op amp model. This LT Spice schematic shows where the input bias current sources are inserted. The bias currents flow into the terminals of the op amp, both of them in the same direction. This means that these are common mode currents. These currents cause a voltage drop across any. In this slide, we explore what the effect of the input bias currents are. Let's assume that the resistances in the circuit are represented by R1, R2 and R3. For the sake of this example, let's assume that the input is shorted on the left of R1 and R3, as shown in the schematic. In other words, there is no input signal to the op amp. As we shall see, both of the bias currents have an effect on the output voltage of the op amp. First, let's explore what the effect of the bias current, flowing into the positive terminal, is on the output voltage of the op amp. This is the input bias current that flows into the top, or positive terminal of the op amp in the schematic. The positive terminal bias current flows through R3 and produces a voltage at the positive terminal relative to ground. This is the expression for the voltage across R3. This voltage appears as an input signal at the positive terminal of the op amp. This means that the op amp operates as a non-inverting amplifier, with a signal applied to its positive terminal. This is the expression for the output voltage, due to this signal across R3. The input to this non-inverting amplifier is connected to the positive input terminal of the op amp, which is the usual way of connecting it. This section of the circuit is shown in red. The feedback circuit of the non-inverting amplifier consists of R1 and R2, and is highlighted in yellow. The output voltage, generated by the voltage at the positive input terminal of the non-inverting amplifier, is given by this expression. Secondly, we explore the effect of the negative terminal input bias current on the output voltage of the op amp. The negative input bias current flows through R2 and produces a voltage at the output. This is the same as with a transimpedance amplifier, which will be introduced later. This is the expression for the op amp output voltage, due to the negative input bias current. This is the expression for the total output voltage, which is the sum of the positive and negative input terminal voltages. This expression also gives us a clue of how to counter the effect of the input bias current. In the next slide, we shall explore how to cancel the effect of the input bias current. We want the output voltage to be zero, which we can achieve by varying the value of R3. In this slide, we explore how to cancel the effect of the input bias currents. We return to the schematic used in the previous slide. The signal generated by the positive input bias current is again highlighted in red. The net output voltage, generated by both the positive and negative input bias currents, is given by this equation. The output voltage, due to the positive input bias current, is given by this expression. And, the output voltage, due to the negative input bias current, is given by this expression. Combining the above expressions, yields the following expression for the output voltage. The requirement is to make the output voltage, due to the input bias currents, 0. This means that the expression for the output voltage, reduces to this expression, containing the input bias currents, and resistor values. This expression is simplified, to obtain an expression for R3, that satisfies the condition to make the unwanted output voltage, generated by the input bias currents, 0. So far, we explored several op-amp characteristics. We added internal poles to limit the bandwidth, we added clipping, slew rate, input offset and input bias current, to the ideal op-amp circuit model. We have built out the ideal op-amp, to include various imperfections. The internal circuitry is shown within the large rectangular box with the dashed line type. There is some external circuitry, outside the box, that we added to counter the effect of some of the imperfections, which we shall identify. Starting from the left, the imperfections are: input bias current. The resistor to cancel the input bias current, shown here as our bias. The offset voltage. The resistor network to cancel the offset voltage, powered from the supply rails. The circuit model for the slew rate. The double pole RC circuit model for the finite bandwidth, which can be simplified to a single dominant pole. The clamping circuit at the output of the op-amp, and finally, the feedback resistor network that we use when we have closed-loop feedback. And that is what our op-amp model looks like so far, with input bias current offset voltage, finite bandwidth and output voltage clamping. This is the schematic from the previous slide. It is the ideal op-amp model, with the various imperfections that we covered so far, added. The LT-SPICE simulation file name is shown in the slide. It is a time domain simulation. Use this LT-SPICE simulation to vary the input signal parameters, as well as the waveform, for example, change the waveform from a pulse to a sine wave. Also investigate the effect of closed-loop operation with feedback, under the above conditions. This is the schematic from the previous slide. It is the ideal op-amp model with the various imperfections that we covered so far, added. The LT-SPICE simulation file name is shown in the slide. It is a frequency domain simulation. Use this simulation to vary circuit parameters and observe the effect on the frequency response. Add closed-loop control, using a non-inverting amplifier configuration, and use the simulation to determine the effect on the frequency response. This brings us to the end of the section on the input bias current. So far, we assumed that the input bias currents are equal. Next, we are going to investigate what happens when the two bias currents are not equal.